an optical microscope, but I'll show you can also use a scanning electron microscope as well to visually see what's going on here. All these different modes. There's contact mode, there's non-contact mode. Usually AFM, why it was originated, was to get the sample topography. But you can also functionalize your tips, and that's what we're going to be talking about today, MFM and scanning NV. There's more advanced modes too. Chemical force microscopy, electric force, Kelvin probe. You can do nanoindentation. It's a immense field, right? Started in the 80s, and it's just gone. It's still very powerful. People are still adding modes that you can do with AFM. So what a basic AFM, the block diagram here. So the probe. Usually people are using cantilevers made of silicon that look something like this. Usually made by some MEMS technique. There's also all different ways you can make these, but they have things in common. People are interested in the spring force, right? It's a little lever. If I push on it, how stiff is it? Usually the longer things are, the lower the spring constant is. People want to know the length, the width, the thickness of these things. The tip is very important. The size of the tip is going to determine the resolution of your AFM. The shape is very important. Is it pointy? Is it elliptical? Blah, 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 blah. Other functionalizations, that's what we're going to be focusing on today. MFM and scanning NV. The force transducer, how do we actually know how much this little cantilever moves? 95+% of AFMs use an optical readout technique. So if this is their cantilever, they make a portion of it reflective, you shine a laser on the back of it, and you have some sort of photodetector to see how much this thing moves. So you can imagine, this is very small, this is so far away, small deflections of this can cause big deflections here, and you can read out how much your cantilever deflects. And if you know how much it deflects, and you know the spring constant, you can determine how much it has moved. Because again, you're interested in the topography of your sample here. You can also use an electrical readout. This is not very common, but there's one manufacturer that I'll show briefly here that is pursuing this, where you can actually put piezo resistors on the cantilever itself and read this out electrically. So as this deflects, the resistance of this changes, the voltage changes. You can do electrical readout as well. Typical sort of force versus distance curve here for AFM. If we just focus on the red curve here, if we're very far away from the sample, the van der Waals forces are basically zero. The tip feels no force. As we move towards the sample, there's this little region of attraction where the tip will snap onto the surface of the sample. And then as we continue to push the cantilever towards the sample, we'll get these repulsive forces, and the cantilever will begin to bend up. So this would be, let's say, a contact mode, in which we have the sample basically in contact. We're seeing how much it reflects here. We can see this in an animation here. Again, we're going to start very far away, and when we come close, it attracts, and then we push farther, and then it repels away. So this would be an example, let's say, contact mode, where we use force, which is proportional to the deflection, as a feedback mechanism. And usually people are working in a realm in which they're constant force, and they can determine the topography of their sample in this way. But for MFM and for scanning NV, we don't want to be in contact mode, we want to be in tapping mode. We'll talk a little bit about tapping mode here. So in tapping mode, we have our cantilever, and we have a little tickler piezo on this end here. We juice this with an AC voltage, and we get this thing oscillating, right? And it's going to have some sort of a resonant frequency to it. So as we scan through the frequencies of this little tickler piezo, we're going to have a resonance condition where the amplitude is going to increase. And the length of the cantilever also dramatically affects the resonant frequency. This can be very important too. Sometimes we want a high resonance frequency, sometimes we want a low resonance frequency. We're going to be doing an AC measurement for both MFM and scanning NV. So again, in this tapping mode here, we excite the sample, and as we get close to the sample, the oscillation amplitude will decrease as we approach the sample. So again, I showed this with some cartoon here. We get close, the amplitude decreases. So as before, for contact mode, you usually use force as your feedback mechanism. In tapping mode, you use the amplitude as your feedback mechanism of this AC technique. And this is very important, and this allows you to get very nice topographic images of samples. Doesn't matter what the sample is. I just threw it up here because it has some topography. Because this is an important first step for both MFM and scanning NV. You have some sample, and you want to sense how magnetic it is. clearly you want to always be the same height above the sample, right? The magnetic field is going to drop off over our cube, right? Sometimes more depending on the domain structure, right? So you always want to fly above the sample at a certain height. And that's going to be a persistent theme for both of these techniques. So with MFM, got our cantilever, what do? We coat it with something magnetic, something like cobalt chrome, usually tens of nanometers of something. You can put permalloy on here, you can put iron platinum on here. People put any of the iron, cobalt, nickel, alloys, whatever you want, you can put on here. People do all sorts of stuff. But we also need to think and be cognizant of the coercivity of what we put on here and the magnetization or moment of what we put on here. This is just one manufacturer of MFM tips and other AFM tips as well. So again, it's not just now the force constant and the resonance frequency, we got to think about the coercivity. So for instance, let's say you want to do MFM in a magnetic field, and you don't want to change the moment of your tip. Well, you got to know the coercivity of your tip, don't you? The magnetization. You're scanning a magnet above your sample. Let's say your sample is very magnetically soft. The tip can affect the sample. Similarly, for some samples, the sample can affect the tip. And we've all played with magnets, right? I mean, it's the same sort of deal, just at the nanoscale, right? There's going to be all these forces at play here. We have to be cognizant of all of these things. So the parameter space with MFM tips is now much larger than a standard AFM tip. And of course, the size of the tip is very important for the resolution as well. So this is also just from the same manufacturer here. Clearly, the pointer tips, which I'm sure cost a lot more, you can resolve magnetic domains much more clearly. Well, let's say you know your magnetic domains are only this size. Why would you oversample your sample something this small? You might as well get the cheaper tips here. So it all depends on what type of domain sizes you're interested in seeing. All right, magnetic force microscopy. Most common technique is a two-step process, really a three-step process. First, you usually magnetize your tip. You have a permanent magnet outside the system, and you just magnetize it, you put it in the field. And then the first step is topography. So topography, you fly very close to the sample surface in this AC mode, where the van der Waals forces are much larger than the magnetic forces. And this allows you to get the topography of the sample. Then step two, for the magnetic contrast, you usually fly anywhere between 20 and 100 nanometers above the sample, where now the van der Waals forces are usually zero. And now you're just looking at the magnetic forces of the sample. So let's go through just sort of a simple demonstration of this. An in-plane magnetized sample shown as follows. This is our sample. These are our little domains. These would be our stray fields. Again, my PowerPoint range isn't great, but this is what they would look like here. This here is our AFM tip. If our AFM tip is magnetized downwards, in this region here, we're going to have an attractive force. So if we look at our resonance curves for attraction, that's going to shift the resonance to lower frequencies. And if we look at the phase of our resonance condition, again, it's going to shift it to lower frequencies. So if we're driving at a fixed frequency, the phase, which for MFM measurements is almost always what people are looking at, is the phase, not the amplitude, but the phase of the response. It's going to decrease somewhat. We move our tip here. In this region here, we're going to have a repulsion, as shown here in blue. Our resonance frequency is going to increase. Our phase is going to increase. We're going to have it here. And if we're parked here, nominally there's no magnetic force in this region here. So there's going to be no change in phase. It's going to be the black curve here. So we take a look at this. Remember, our forces are always proportional to the gradient of the magnetic field. That's what we're most sensitive to here, is the gradient of the magnetic field. Gradients are strongest here, here, and basically zero here. And if we look at the phase as we go across our sample, it's going to look something like this here. Neutral, here the phase decreased, got darker, here the phase increased, it got lighter, and then darker here. So interestingly, for in-plane magnetized samples, most of the contrast actually comes from the domain wall region. It's the opposite for perpendicular magnetic samples, in which case you're mostly focused on the domains themselves. I'll leave that for an exercise for you to do later. But it's somewhat confusing when looking at some of these images, because you're not really, again, you're proportional to the gradients of the local magnetic fields, and for an in-plane magnetized sample, it's more or less the domain wall regions that you're mostly sensitive to. So it can be a little confusing sometimes. Just some contemporary examples of MFM that I pulled up. perpendicular magnetic anisotropic materials give you very beautiful domains. This is some results that were measured in field. So again, when you get the PDF, you can just click on this and it'll take you to the paper. Spin ices, very important, very interesting. Seem to be picking up interest in the field now, studying these little stadia, their domain configurations. Stormions are big right now. So this I pulled, this is actually an archive paper. I actually think the lead author is maybe one of the students here. I don't know who it is. I was told he was here. So this may look familiar to you. So a very useful technique. And this is not a contemporary example, but it's one that's very close to my heart because I studied magnetic vortices when I was a graduate student, and that's magnetic vortices. So this is actually a very early result in science where they saw the vortex core in the MFM images. And my PhD advisor would always correct me when I just said there. He would say, they're not actually viewing the vortex core. This is this region of magnetization that points out of plane. But remember, they're imaging the stray field of the vortex core itself. The vortex core is actually quite small, but this fountain of stray magnetic field that exists above the core is actually what you're measuring there. And the region around the vortex core, there's very little contrast. And some of the cores point up, some of the cores point down. But again, I always thought this was a very beautiful image of magnetic vortices. And it's a good reminder of what is the resolution of MFM. Round numbers here, 30 to 50 nanometers. Some people, you can get better, but you gotta work very, very hard. Run-of-the-mill MFM, we're talking 30 to 50 nanometers or so. That's because you have a tip, certain curvature to it. The tip is coated with this magnetic material. If you're flying, the farther away you get away from the sample, the less resolution that you have. You can't fly too close to the sample because then you get those van der Waals forces. You can get other electrostatic forces which can dominate the response. So there's balancing it. Round numbers here, 30 to 50 nanometers, certainly better than MOOC, is what I'm trying to get at here. So many manufacturers of MFMs and AFMs. Pretty much anybody does an AFM does an MFM. I probably missed some here. A lot of these companies buy each other out, etc. And there's even a new company in play here for MFM and AFM, and that's quantum design. Yeah, we're back to the commercial here. Just some water for this next portion at the top. Our newest product, we launched this about 1.5 years, maybe 2 years ago, is Fusion Scope. This is what Fusion Scope looks like. It's pretty small, it's about the size of an ATM here. So what is Fusion Scope? At its heart, Fusion Scope is a scanning probe microscope with all your standard modes: contact mode, dynamic mode, tapping mode, MFM, conduction AFM, etc., with an SEM built around it, a scanning electron microscope built around it. So the idea is we're fusing multiple techniques together. We're doing correlative microscopy in a system like this. The other nice thing about Fusion Scope, so this here is the SEM column. This is representing the SEM electron beam. This here is our AFM cantilever here. We can rotate this and tilt this so that we can look at our samples and our cantilevers on edge. And this can be very important for certain types of samples. So for instance, I'll show you some data here. Now this, a lot of times when I show this, people think this is some rendering, something we made in SolidWorks or something. No, this is actual Fusion Scope data. This is SEM data. We did speed it up a little bit. So we're looking down on the AFM cantilever, showing here. This is our sample. This is actually a piece of bone. Okay? Nobody here is going to be looking at bone, but it's a nice, weird, very bumpy sort of sample here. And what we can do in Fusion Scope, we can actually rotate this in real time and take a look exactly using the SEM of our cantilever and our tip. So if you have a sample which has a lot of variations in height, those of you who have done AFM, you can easily break your tips if you run into something. You can precisely position your tip exactly where you want it. And you can always monitor your tip. Sometimes you're doing AFM and you're like, oh, all of a sudden my images look like crap, right? It's like maybe you picked up something. Well, then you can use the SEM to actually image your tip in real time as well. Something you can't do with an optical microscope. And we're able to do this because we're actually using those self-sensing cantilevers with electric readout. There's piezo resistors on this cantilever. So we don't have to worry about shining a laser on here and getting the response out that way. Because there's no way we could rotate that, there's no way we could put that in an SEM. So it's all electrical readout as well. Of course, we're doing MFM in here now. It's still fairly new to us. We're using this focused electron beam-induced deposition on our tips so we can get very high resolution here. This here's more just a marketing sort of video of MFM, just a cobalt palladium multi-layer that gives you nice Labyrinth domains. But you can do, there's your first pass where you're getting the topography, and then you lift and you do your magnetic signature up here. You just sort of alternate. And you can watch this in real time happen in something like Fusion Scope. It has a shared coordinate system, so you get a broad view of your SEM. You can just click and drag your region of interest and do AFM, MFM there, or there, or there. It's just an example, some spin ices. And again, correlated microscopy. We're correlating magnetic measurements on topography on SEM. Not exactly out yet, but we're also putting in EDS system in Fusion Scope as well, so we can do AFM, MFM, SEM with chemical sensitivity as well. Again, fusing things together. Some brief references on MFM. This is kind of an older one. Lots of history here. More of a contemporary view of the frontiers of some of the things that they're doing now at MFM to improve sensitivity and resolution. And actually, this YouTube video from NanoSurf, I think, is quite good. It goes through things very pedagogically. In this example here, he's showing what happens if you use an MFM tip, which is too magnetic, and it actually writes its own signature into the sample, whereas this is not so good. Anyways, great YouTube video. It goes through a live demo. 15 minutes for scanning NV. Any questions? No. Okay. All right, scanning NV. What is an NV center? A lot of what I'm going to show you in these next few slides is actually from a company called Chi-Feng. They're out of Switzerland. And it's actually somebody, fund design, we sell for them in a lot of international markets, including the United States. So we're good friends with Dumas, so I've used a lot of their stuff because they've been doing this for a while. The core is built upon an AFM, tapping mode, just like with MFM. Now our cantilevers, though, they have diamond tips. Okay? They're not your standard silicon nitride tips. They're diamond. Zoom in here. This is a schematic of diamond. The black circles are carbon. And with an NV center, what is an NV center? In this lattice of diamond, taking away one of the carbon atoms and replace another one. Well, actually, taking 2 carbon atoms away. One we leave empty. One is now a nitrogen atom. This is the NV center. Technically, this would be denoted in NV superscript 0 system, but it can grab an extra electron. And technically speaking, it's a 2-electron system. And we call it NV minus system here. What we want to do here, and there's a lot of magic in the way that they make these cantilevers, is ideally you want to have a single NV center inside this tip. It turns out these exist, they're broadly known as color centers in diamond, and there's a wide variety of them. If you just take a run-of-the-mill piece of diamond and you shine, let's say, green light on it, it will fluoresce red, and you can have multiple. Just in standard diamond, these NV centers which fluoresce here. We're only going to be focused on a single NV center inside of this diamond tip. And we're going to show you how it can be a very sensitive magnetic field sensor. All of this here, we're going to super simplify our energy landscape. This is now basically an energy landscape. We've got a ground state and an excited state that goes into a continuum. And those of you who do this for a living, you've seen how I've oversimplified this, but that's all we need for today. Okay. So, this is our energy landscape. Our ground state, again, it's a 2-electron system, is actually split as well. Spin up and down, exists a little higher energy than the spin 0 state here. And they have a difference of 2.87 gigahertz here. This natural splitting occurs because of the crystal symmetries and the crystal fields existing in this diamond here. We don't need to worry about why this exists, just know that they split here. We shine green light on the system. It's then going to fluoresce in new red. Come in with green light, just like my laser pointer, and we see how much red light comes back. If it comes down into this spin equals 0 state, we get a relatively large amount of red light. If it comes down into this state here, we get less light. So how do we get the system into this state here? We can come in with microwaves. And if we resonantly come in with microwaves, we just put a little antenna next to this, we can get up into this state, and now we have less energy here. We're not going to go into the details of why this fluoresces less. It has to do with the shelving state. There's a lot of extra details there. But all you need to know is if we sweep through our microwaves through this 2.87 gigahertz, all we're doing here is we're looking at the amount of red light that we get. A lot of red light, resonance condition, less red light, off resonance, more red light again. All we're doing here. It's actually a relatively simple experiment. The best contrast you can get here is about 30% or so. This is maybe 25% or so contrast here. And now we're going to see how we can actually use this as a magnetic field sensor. Actually, it's a pretty elegant little technique that somebody discovered. So, now let's apply a magnetic field. Now we're going to Zeeman energy. We've split this spin system here. +1 goes up, -1 goes down. We now have two transitions here. So now when we sweep through our magnetic fields, we're going to get two dips. The spacing between these dips is then proportional to the local magnetic field. It's a self-calibrated field sensor, calibrated basically by quantum mechanics here. So as you fly this little sensor above the sample, you view this little, it's called ODMR, optically detected magnetic resonance, and you look at the spacing between these peaks, that's going to give you the local magnetic field. Funami, they sell different cantilevers with different orientations of the NV center. So you're sensitive along the NV center axis. So if we go back here, you're sensitive along this axis here. So the crystallinity of your diamond determines what field vector you're sensitive to, in essence. Okay. So they sell tips. The most common tip would be like this, so you can actually measure both the in-plane and out-of-plane components of the local magnetic field. But sometimes you might want an NV center like this or like this, depending on your sample and what the local magnetic field is doing. If you're real fancy and you're very good with math and you're looking at some other higher order effects here, you can actually get two components of the magnetization out as well. It can be a vector magnetometer as well. Block diagram of a scanning NV center. Again, the core is an AFM, scanning the sample. It's an AFM though, special tip, and a confocal microscope. So green light comes in, that's not shown. The amount of red light comes back out, and we just analyze with an APD how much red light comes out as a function of microwaves. And there's a little antenna that you want to get very close to this NV center here. What do these tips actually look like? They look like this. These are the ones from Funami. So this is all diamond. And again, with the magic of nanolithography, they're able to get these pillars and they're able to plant a single NV center right at the tip here. The idea is you want to get it as close to the tip as possible because that's where the resolution is the highest. But it works just like a standard AFM as well because you work in that tapping mode so that you always fly above the sample at a certain height. I will say though, as an AFM, it's not very good. The ladder resolution is not very good. This is very blunt. It doesn't look like it here. It's pretty small, but it's actually quite blunt compared to most AFM tips. But it's good enough that the cantilever flies at the same height above the sample. Yes?
So for every pixel you measure, the microwave frequency also is varying?
Oh, yeah, now this is a good question. There are different modes in which you can measure. What Funami would call the full quantitative mode, yes, every pixel you're going to measure something like this. Sometimes you can measure just a single peak and see how it varies. Sometimes you can park just at a single frequency. If you know that the local magnetic field doesn't change very much, if you just park here, you can look at this intensity here. So yes, the measurements do take a very long time compared to something like MFM. Because in the best world, the most data, in each pixel, you're getting a data set that looks like this, so that you can do this. You can also do a mode called quenching mode, and we're getting into details now, where you have very high magnetic fields, and you're just looking at this intensity. So you actually don't even care about the microwave excitation, and you can tell something about the local magnetic fields. So there's all sorts of different modes, but the most full quantitative mode, it's slow. So I would say, round numbers here, MFM versus scanning NV, order of magnitude longer in terms of measurement time for the full quantitative mode. Yeah.
Thank you.
A lot more data as well. So you must gain something from it, right? You would call that time and expense. So I'll show you what you gain from scanning NV microscopy as well. This here is actually using the confocal microscope, looking at the top of this here. So you can see that's the pillar. You're actually looking at the pillar from this side, shining green light, and then this is the fluorescence, how much red light. And this is the light from a single NV center at the bottom of this cantilever here on this tip. And they actually fabricate this so it's also a light pipe, essentially, like a fiber optic, so you get maximal light out of this. Very, very impressive that they can make this. Not trivia at all. Just some example data. We're running out of time with NV center work. This is all Qnami data. Where does NV centers really become important? Ultra high sensitivity, things like antiferromagnetic domains. Skyrmions, very important. Defects in nanowires. Very small changes in the magnetic field. More examples. So this, I showed this earlier. Skyrmions as well. This is that archive paper here where they do MFM and scanning NV. Here's some couple of the first works. I think these are from 2006. Cryo scanning NV center microscopy as well. Superconductors and vortices and superconductors as well. So you can do these at low temperatures, high temperatures. These cantilevers are actually quite robust. But again, the infrastructure starts to get much, much more complex. It's not as easy of a technique as MFM. Who are the main commercial equipment players in this field? We talked about Qnami out of Switzerland, Q-Saber out of Switzerland, C-Tech out of China. They're all working on low temperature versions as well. And that's what an important variable to be able to change. NV Center YouTube resources. This is a great YouTube resource out of Brzezinski Galich out of Santa Barbara. If you want to go into more details about all those different states that I glossed over, this is a great YouTube video. And anything from Ronald Molesworth is also great for NV Center stuff as well. MFM versus scanning NV. All right. Both of them are based on a conventional AFM. Both of them you can do in applied magnetic fields, in ambient or vacuum conditions, and at variable temperatures. It's kind of critical that you be at vacuum to change the temperature. Pros, ubiquitous. Right? Anybody who's doing AFM, you can pretty much do MFM. Cantilevers are relatively inexpensive, well established. People have been doing MFM since 1987. This is still a relatively new technique, but the pros, better sensitivity than MFM. Slightly better spatial resolution than MFM. The nice thing I like about scanning NV is the tip does not affect the sample. Right? It's not a bunch of magnetic material on a cantilever. It's just a little defect in diamond. It does not affect the sample. I also like that you're directly measuring the field with scanning NV. Here you're measuring the field gradients. Here you're literally just measuring the local field, and you can get a value out in Gauss. A little complicated giving all the directions and the vector components, etc., but you can get the vector capabilities as well if you do your math and you make some assumptions. Right? Here, the tip can alter the magnetism of the sample can alter the magnetism of the tip if you're not careful. And again, it's sensitive to the field gradient, not the field direct. Cons here, still relatively new technology. The cantilevers are a good order of magnitude, plus more expensive than an MFM tip. As you can see why, they're made of diamond, they put single NV centers in there, thousands of dollars for a single tip. It's built on a conventional AFM, but you do need to have confocal optics as well. And I will say, reading more about the scanning NV stuff, some situations, perhaps it's a little bit too sensitive. You can quench this effect if you have a magnetic field perpendicular to the NV axis. So let's say you've got a perpendicular magnetic anisotropy film with a elaborate domain, very strong magnetic fields. This might be too sensitive. You might have to work in something known as quenching mode. You might be better off with an MFM. And as that archive paper I showed a couple of times showed, both is good, right? Not one does everything. Maybe you want to use both. They both excel in different regions and different parameter spaces. Depends on your sample. All right, so this was our journey through space and time. 6 different topics. Hopefully something new for some of you. Hopefully not too much of a commercial. But that I did what I could do. Some additional few resources for your bookshelf, books that I like that I didn't show earlier. Absent in today's talk was anything dealing with X-rays and XMCD. I thought about putting it in, we just didn't have time. But if you want to do, and you want to learn about XMCD, this is the book for you. I remember reading this cover to cover as a graduate student. Storr's book on magnetism does a lot of stuff with X-rays. It's a great resource. So I can't recommend this high enough. But really all of these, depending on what you want. If you want to, there's a chapter here devoted to magnetic materials that is great. If you want to know what the magnetization of permalloy is and its function at temperature, he's got it in there. This is also a great resource. And historically, everybody knows Cullity as well. I look at this one less these days. So. All right, quantum design, how to keep in touch with us. Follow us on LinkedIn. You might see your picture on there later today. And our YouTube channel. Okay, if you've got a piece of quantum design equipment, one plus side of COVID era was we couldn't travel. I couldn't come see you guys, right? So we put a lot of content online. If you have the VSM or one of our measurement options, we've got a bunch of webinars devoted to this. You can watch this stuff on demand. We also have more commercial things. You want to learn more about fusion strip, we've got a video on that. Lots of content here. Like and subscribe. It's not a monetized channel. Smash that like button if you guys see something like this. But do follow us on LinkedIn. If you want to find out what the next new thing is, LinkedIn is where it's at. If you're interested in a job, that's where we post things like jobs, etc. Follow us on LinkedIn. I also want to just highlight our own school. It's not a summer school, it's a winter school, right? We didn't want to compete with all the summer schools out there. And who doesn't want to come to San Diego in winter? It's going to look exactly like this, it always does. We had our last year we had our inaugural winter school. We bring in 6 students, so it's a very exclusive school. The idea is you have to get yourself there, but we will put you up in a hotel and feed you for a week. Give you access to our beautiful applications lab where we have a Dynacool, a Versa lab, an MPMS3, a fusion scope, and a few other things. Come with samples, learn how to use stuff. You can apply by sending an email with your CV along with a statement describing how measurement equipment offered by quantum design is a critical part of your research and how you would benefit. Get that to us by November 1st. We'll get back to you by December 1st. We had a lot of applications last year. Again, it is we only got room for 6 people, so it's a very exclusive school. We can't host this many people because it's in our lab. We only have so many pieces of equipment. And it's meant to be a hands-on school. Lectures in the morning for an hour and a half, and then we're in the lab doing stuff. Right? So again, very successful last year. We're going on an excursion. Again, those of you in the States, you know, you're in, I don't know, anywhere other than San Diego, it's going to be cold. It's going to be beautiful. February is a beautiful time to be in San Diego, and we're looking forward to our 2nd annual winter school. And with that, I'd like to thank you for your attention. I'll take any more questions.
Just about the NV Center-based MFM, I'm wondering that compared to NV Center diamond, there's also another materials like just some doped glasses. You can also emanate some fluorescence. And what's the advantage to fabricate such an NV Center-based tip? Yeah, so that's my point.
I don't know of any others, I guess is what I would say. I would say that these NV centers are very well characterized. They've been around for a while, I mean, tens of years now. I'm not sure what these other, I mean, a lot of things fluoresce, but they also have to be sensitive to the magnetic field. And this NV center, in particular, is NV superscript negative, minus, which everybody was colloquially called an NV center. It's very special because it's what's actually, because we have that spin split, we get that spin triplet, so we have the +1 and -1. That's going to be sensitive to the magnetic field. You have to have something like that. For instance, these tips, they're the NV minus tip. I've heard stories, I haven't personally observed this myself, but I've heard stories that say you're scanning over samples which are not conductive, they charge up. The NV center, if it's too close to the surface of the diamond, can actually, you can lose that negative sign, and all of a sudden it's an NV superscript 0, and now it's not sensitive anymore. So it can actually just magic, I keep using the word magic, I mean, it somehow grabs an electron, or sorry, loses an electron, and now all of a sudden it's an NV0. and all of a sudden, everything's gone, all the sensitivity's gone. So you really, it's a very specific sort of thing with these NV centers. So I don't know if it's ubiquitous, if there's more examples of it. I'm not that much of an expert in that field to comment further. But I do know that people are studying these in great depth. And these NV centers, people are also using them. They can also be used as qubits. Very, very advanced stuff. And you could angle them. Now we're in a realm that I can't even think about talking about right now. Because I also don't know anything about it. So it's easy. But yeah, there's lots of things that you could do.
Okay, thank you. Clear.
Any more questions? Should I have one, maybe?
Right.
So for the MV Center, when it was first rediscovered, it was branded like a good media for quantum computing. So what's your take on that? Because it turns out to be more like a metrology means in the end.
Yeah, no take.
No take?
Yeah, I can't comment on the quantum computing stuff. I mean,
I see.
everybody's got their different qubit, right? Everybody's very provincial about them. You know, some are superconducting based, some are trapped ions, these NV center ones. The nice thing about the NV center ones, I guess, right, they work at room temperature, which is great. I don't know if there's any benefits in lowering the temperature of them, but now we're so far out of my realm, you know, I barely remember Schrodinger's equation, right? I can't, you know. But as far as a magnetic field sensor, what I demonstrated today with those energy levels, that's what I got. That's all I can comment on.
Any further comments?
Could you comment on STFMR?
You want me to spend an hour on STFMR measurements? Is everybody good with that? One more hour?
Yeah, maybe like benefits, pros and cons.
Good question. So, all right, STFMR. I don't have any diagrams for this, but STFMR is a variant of ferromagnetic resonance, right? Where now you come in, usually, so the ferromagnetic resonance I demonstrated was for like blanket film. STFMR is usually done in devices where now you use there's a field component, but there's usually a spin torque component where you have a device in which you juice it with the RF current, right? And due to spin torque effects, you can induce magnetization precession. That induces a voltage response, basically a rectification response in the sample that you then measure. So it's basically STFMR is a way to do FMR on the local device level of a sample. So you usually need devices, and the idea is you come in with microwave current. You need to have the right kind of sample. Not all samples produce spin torque, right, to produce magnetization precession. But at the end of the day, you juice it with RF microwave current, usually also a DC current as well, to sort of loosen things up, and then you measure a voltage as a function of frequency. And you get similar sort of responses, and it's a great way to locally measure FMR in devices. Without further preparation and images and diagrams, I can't say much more than that. But STFMR would be a good thing to add to this talk as well. It's a very powerful technique that exists in that same, I would say it's in the same family as this broadband FMR sort of landscape. But again, it's for devices generally. You need a pattern or something.
So let's thanks Randy again. And we'll be announced for 1 week. We'll have questions. And just a little bit more public announcement. So we saw the larger demand of veggie food. So starting from tomorrow, we'll have more, one more vegetarian table. So hopefully that can accommodate all the demands. And for tomorrow, we're going to have excursion. So we'll have 3 tour buses near the entrance of, you've been here before, so you know that there's a parking lot